Hello everyone. In this session, we will be doing two new terms called modulus of a complex number and next would be argument of a complex number. So let us start first with modulus of a complex number. So what should be first thing? Let us define what we mean by modulus of a complex number. And the definition says that if z is a plus ib, then modulus of a complex number is denoted as those two lines, and between them we write as z, and that is called actually mod z, and mod z is defined as under root a square plus b square. The moment you see under root a square plus b square, you realize it is a non-negative quantity, right? So modulus z is a non-negative quantity. Remember this. Now, if I take in place of a plus ib simply a, means if b is 0, then what will happen? That under root a square plus b square will simply reduce to under root a square, and that is nothing but absolute value of a, that we have already done in chapter called equations in equations, right? So in case of a real number, we have denoted same thing as absolute value and name was different. Here we call it modulus in case of complex numbers, and in case of real numbers we have called it as absolute value. Okay, so let us proceed further. Take one quick example. An example says if z is 3 plus 4i, then what is corresponding modulus of z? And it would be nothing but under root a square plus b square, so under root 3 square plus 4 square, so answer should be 5. And if z is minus 7i as my second example, mind you please, same thing we'll be using. A is 0 here, so mod z would be under root of minus 7 whole square. Remember, don't write answer as minus 7. It should be absolute value of minus 7, and hence answer is nothing but plus 7. So, now proceed to properties of modulus of a complex number. Now, first property is that modulus of z and modulus of z bar, they are same, because answer for under root a square plus b square and answer for under root a square plus minus times b whole square would be same. So mod of z bar and mod of z, they are same. Now next is z bar equal to mod z whole square. Now this is extremely important property which connects conjugate and modulus. So there are some questions where question is in the form of modulus and you have to use this property and go to conjugate part and solve the problem. Or it could be other way also. Conjugate is given and you have to use this property to reach to modulus. So z bar equal to modulus z whole square. The next one is mod of z1 z2 is mod z1 into mod z2, means modulus of product of two complex numbers is product of their moduli. The next one is mod of z1 upon z2, which was expected in the cube, right? So mod z1 upon mod z2, obviously z2 not equal to 0. Now these next two properties what I have written, they are z1 plus z2 and z1 minus z2, their moduli. Now both are less or equal to mod z1 plus mod z2. More explanation of this or more understanding of these two properties you will have when we go for geometrical interpretation also. So let us not spend more time here. Just keep in your notes that these two properties are also important. And the next one, which is very rarely used property, but keep in your collection, and that is mod of difference of the moduli. That means mod z1 minus mod z2. Its modulus is less or equal to mod z1 plus z2. Now this seventh one is less used, but it has to be in your notes somewhere. Rest all are comparatively easy also to remember. Now I go further and take one illustration on modulus. And actually that example, my illustration looks quite lengthy. Mod of a z1 plus b z2 whole square plus mod of b z1 minus a z2 whole square equal to, you have to show a square plus b square into mod z1 square plus mod z2 square. This example I am only taking to make you realize that how those properties, just now what we have seen, are to be used in solving this particular example. So let us start. What we do is, I start one by one. Mod of a z1 plus b z2 whole square. First I take only this part. And I realize I can use mod z square as z bar. And I use that property and I write a z1 plus b z2 into its conjugate. And then a z1 plus b z2's conjugate, that also we use. How to write? It would be a z1 bar plus b z2 bar. Mind you please, A and B are real. So their conjugates are not to be written. It is to be written as A and B only. So when I write in next step, it would be A Z1 bar plus B Z2 bar. And the first bracket still remains same. Now you can actually multiply them term by term and get A square into something plus B square into something as I have written there. So there are basically three terms. One is of A square, one is of B square, and one is of AB. Now I attempt the second part, that is mod of BZ1 minus AZ2 whole square. Okay. Now to get this again, we will be using similar property, that mod Z square is nothing but ZZ bar. Same property I will be writing and simplifying it term by term, and I will get again here also term of A square, B square and product AB. What is our job? Left hand side says that we have to add these two quantities. So when I add these two quantities, I will be getting nothing but A square plus B square into mod Z1 square plus A square plus B square into mod Z2 square. So A square plus B square can be kept outside, take common, and this leads to mod Z1 square plus mod Z2 square. Mind you please, this is nothing but your right hand side. Now it looks as if like now everything is over. My emphasis is this particular property is important. It has some geometrical interpretation if you take precisely A and B as one. And this property then looks quite decent, and that is nothing but mod Z1 plus Z2 whole square plus mod Z1 minus Z2 whole square equal to twice of mod Z1 square plus mod Z2 square. Now when we go for geometrical interpretation, this result turns out to be extremely important and nice result to be remembered. Now this particular property is also called as Apollonius theorem. You remember, this is something what we have seen in real numbers also, and this is also named as law of parallelogram. Now I'm not getting into more details because we have not yet done the geometrical interpretation. When we do geometrical interpretation, this result would be extremely, like beautiful to understand also. So from here I proceed further to argument of a complex number. This is also a new term, and mind you please, actually modulus and argument, they are heart of complex numbers. You must understand argument clearly, because at many places argument, you just write 2 or 3 sentences and you think that you have learned. No, it takes lot of time because it has lot of deep meaning in argument. So let us first define what we mean by argument of a complex number. The definition is that if I have z equal to a plus ib and mod z equal to r, now you know what we mean by mod z, then, and if a real number theta exists such that a is r cos theta and b is r sin theta, means you have to search some theta which will satisfy this, that given complex numbers real part is equated to r cos theta and given complex numbers imaginary part is to be equated to r sin theta, and we are in search of such theta. Mind you please, even if I have written here r, that r is to be replaced by under root a square plus b square, so it's a known number. So this would be nothing but 2 equations. One will have sin theta in it, another one will have cos theta in it, and you have to search what is that corresponding theta. Now the thing is, definition wise this theta is called the argument, true. My emphasis was on this part, that many people go from here because they have to find theta, they go for tan theta by division and then they try to find out theta, which is extremely wrong procedure to find theta. Those who have hold on trigonometry, they will understand what I mean, that you cannot just divide one by other and get tan theta and go for theta, right? So when we find argument in questions, again I will be emphasizing on this point. Now what we observe here, that theta can take multiple values. Why do I say so? Because we have seen in trigonometry, if I have sin theta equal to half, then theta equal to 30 degree or theta equal to 150 degree. So there are 2 values which will satisfy sin theta equal to half. So theta can take multiple values. So it is not one value which will satisfy. Secondly, also, if you recall in trigonometry, we have seen sine and cosine functions are nothing but periodic functions. So if theta is a value which satisfies, then theta plus 2n pi is also another value which will satisfy. So that also will be called an argument. Next, if theta lies between minus pi and pi, then that is called principal argument. This is a special term name given to particular theta which lies between minus pi and pi. Frankly, theta can have multiple values. This you must understand. And if question is regarding principal value, then you will have to search theta, which is between minus pi and pi. Okay, now I proceed from here and I take one illustration. Find argument of z if z is 1 plus I and then second is z is 1 minus I root 3. Now these are two different questions. I have taken deliberately in which one is like real and imaginary part both having positive sign, and the other one is they have another, different signs. Now first I write 1 plus I as a plus ib, and I write correspondingly what is a, what is b, and I go for mod z because that would be required. I have to get theta such that now a equal to r cos theta and a is 1. So 1 equal to r cos theta and b is also 1. So 1 equal to r sin theta. What is r? That is mod z. And what is mod z? That would be under root of 1 plus 1. It is under root 2. So what we are finally left with? Cos theta equal to 1 by root 2 and sin theta equal to 1 by root 2. Now cos theta and sin theta both have positive signs. That means that will happen only in the first quadrant. So theta will have to be pi by 4. So argument of z, which is nothing but theta, will be nothing but pi by 4. If you add 2 and pi to it, still answer still remains correct. Now when I have written here argument of z, I meant nothing but principal argument. Now I go for that 1 minus I root 3 part, which is the second one. Here also I write a, b separately because we are doing it for the first time. A is 1, b is minus root 3. I will again write nothing but that I have to find out theta such that 1 equal to r cos theta and minus root 3 equal to r sin theta. What is r? R is under root a square plus b square, which is mod z. And that is nothing but under root 1 plus 3. So answer for r is 2. So will this give you two equations in sin theta and cos theta? Yes. My equations are cos theta equal to 1 by 2 and sin theta equal to minus root 3 by 2. Now understand, sin theta negative and cos theta positive. Where does that happen? Remember, in trigonometry we have done sin theta negative, cos theta positive. That happens only in the fourth quadrant, and hence theta is nothing but minus pi by 3. So answer for argument would be minus pi by 3. This is how we have found arguments. Now let us proceed from here and go to properties of argument. Now I am doing it at a stretch. Please, you can take one break and take more examples and first get hold on finding arguments, right? And then go for properties of argument. Now, what are the properties? Now, I have drawn here figure so that I have not yet done geometrical interpretation part, but when you see something in picture form, things are, better to understand. So, I am drawing here axis and I am taking properties one by one. I take first, I had shown there one point on horizontal axis, and that there I write, I have deliberately written here RE as if like that axis, what I have shown horizontal one is named for the real part only. If z is greater than 0, the moment I write greater than 0, that means we are talking about real numbers. That means z is real and a positive one. So obviously it comes on the right hand side of vertical axis. So what would be corresponding sin theta and cos theta? Sin theta would be 0, cos theta would be 1. And in this case, what would be corresponding theta if I have to write? It will be nothing but 0. So argument of z is 0 whenever z is a positive real number. So I have just shown the figure part so that you should not just mug up those properties. Otherwise, I could have written one by one the properties of argument. First property is argument of z is 0 whenever z is a positive real number. Now, what happens if z is an imaginary number? Then next would be something regarding the imaginary one. Argument of z is pi by 2 if z is purely imaginary and imaginary part of z is positive. The moment I say imaginary part of z is positive, that number would be marked above horizontal axis on the vertical axis. Then only imaginary z would be greater than 0. More hold on this you will get when I take separate session on geometrical interpretation. So since your point is on the vertical axis, so corresponding sin theta is nothing but 1 and cos theta is 0. And when does that happen? Whenever theta is pi by 2. So argument of z is pi by 2. Let us move quickly in the similar manner for nothing but z less than 0. So point would be marked on the left side of vertical axis, and we are taking a negative real z, and sin theta is 0 and cos theta is minus 1. When does that happen? Whenever theta is pi. So argument of z is pi whenever you have a negative real number. Okay, next property is about, which is now expected, the fourth point on the vertical axis and below horizontal axis, and for that cos theta would be 0 and sin theta would be -1, and that is only possible whenever theta is minus pi by 2. So argument of z is minus pi by 2 whenever z is purely imaginary and imaginary z is less than 0. Mind you, please, those who are finding that geometrical part right now difficult, they can just remember the properties. When we do geometrical interpretation part, then you get back to this and try and understand what these properties are and how they have been derived. Okay, so let us move further from here. Now, if z1 and z2 are two non-zero complex numbers, then what about the argument of the product? Argument of z1, z2 is argument of z1 plus argument of z2. What is next? As expected, argument of z1 upon z2. It is argument of z1 minus argument of z2. Now, these two properties, when you see, I mean, do you recall anything? They look something similar. We have already seen. Stretch your mind. Till then, I write the third property. And third property is argument of z raised to n equal to n times our argument of z. Those who have understood that how those two properties look like logarithm, you have seen similar properties, they immediately would lock the things saying, yes, these three properties look like nothing but what we have done in case of logarithm. This I am just giving you. I mean, no, this is just some, like similarity I am giving you so that you can remember them. You have done something similar result before, so you can remember. Otherwise, frankly, there is no such connection between log and argument. Please do not misunderstand me what I am saying here. So these three properties are important. We will be using them again in problem solving later. Now from here, I go for illustration as expected, because now a lot of theory part I have covered. Now my first example is that we have to show argument of z minus z bar. It is nothing but plus minus pi by 2. When you see the question something like z minus z bar, so from where to start? Now first thing is, I mean, what comes to your mind is z equal to x plus iy. I will write z bar as x minus iy. Nothing wrong about it. You can always write, go for z minus z bar, and you get this is nothing but 2iy, right? And y is real number. So 2iy is a purely imaginary number. The moment you say it is purely imaginary number, what would be its argument? Just now we have done in the properties. Whenever you take purely imaginary number, whether imaginary part is positive or negative, once it was plus pi by 2, otherwise it was minus pi by 2. So argument of z minus z bar, since 2iy is purely imaginary number, answer would be plus minus pi by 2. This, I mean, steps are nothing. This is only by understanding and remembering properties. You have to use the correct property at the correct place. Now let me take the next example, and the next example is show that argument of z minus argument of z bar equal to plus minus pi if z is purely imaginary. Okay, so z is purely imaginary, that is given to me, and I have to find argument of z minus argument of z bar. Now if I am saying z is purely imaginary, so obviously something into I will have to write. So I do one thing, I write z equal to bi, and also I understand that z bar is also purely imaginary. So if I am writing z as bi, and if I take b as positive, then corresponding z bar, which is minus bi, that will be a negative quantity. Okay, so argument of z would be plus pi by 2. Why? Because b positive. So you have imaginary part positive. So corresponding argument has to be plus pi by 2. And argument of z bar would be nothing but minus pi by 2, because that imaginary part is negative. So argument of z bar would be nothing but minus pi by 2. And what we are asked to find out? Argument of z minus argument of z bar. Argument of z minus argument of z bar in this case would be pi by 2 minus pi by 2. So that will be nothing but plus pi. Now this part I have done taking b positive. So obviously we will have to derive the second part. If b is negative, then what? So I go for b negative. I will write similar steps, and I will understand that argument of z minus argument of z bar in this case would be nothing but minus pi. So answer is either plus pi or minus pi. So I think we are through in this particular example. So when we meet next time, we will be doing again something new. Till then, please revise and then come for the next session, and stay tuned. Thank you so much. for watching this video. If you have liked the video, please click here to subscribe. And if you wish to buy the book, you will have to click on this side. Thank you.